Welcome back to AI.Code.Cast.
Yeah.
We love to take deep dives, and today we're taking a deep dive into a coding problem that one of you amazing listeners sent our way.
Yeah.
It's a classic.
Absolutely.
It's all about finding every single subset of a set of unique numbers.
That's right.
We're talking the power set.
You're absolutely right. This problem is like a staple in coding interviews and algorithm challenges.
Yeah.
It seems deceptively simple at first, but
Yeah.
it can quickly spiral into a complexity monster if you're not careful.
So let's paint a picture for our listener.
Sure.
Imagine you have a set of numbers.
Okay.
Let's say 1, 2, 3, just for simplicity.
Right.
The goal is to find every possible combination of these numbers you can create,
Yep.
including the empty set
Uh-huh.
and the set itself.
Okay.
No repeats allowed.
And that's where the real fun begins.
Yeah.
The number of possible subsets explodes as your set grows.
Yeah.
It's like a mathematical chain reaction. For a set with n elements, you'll end up with a whopping 2 to the power of n subsets. That's 2n for all you math whizzes out there.
Whoa.
Yeah.
So if we just try to brute force our way through it,
Right?
like listing out every single combination,
Yeah.
we're going to run into trouble pretty quickly,
You will.
especially when those sets start getting larger.
Exactly. It's like trying to list every grain of sand on a beach.
Ooh, that's a good one.
You need a smarter strategy.
All right, so if brute force is out the window,
Right.
where do we even begin?
Okay.
Any hints you can throw my way?
Well, think about how subsets are built.
Okay.
You're essentially making a decision for each element. Include it or don't include it. What programming concept comes to mind when you think of making a series of choices?
Choices.
Yeah.
Decisions.
Yeah.
Are you pointing me towards recursion?
You got it. Recursion can be a powerful tool for exploring all the possible paths in this problem, kind of like navigating a maze.
Okay, I think I'm starting to see the light here.
Mm.
But before we dive into recursion, let's take a step back and try a more intuitive approach.
Okay.
We could build our subsets step by step, like adding bricks to a wall.
That's a great idea. We could start with an empty set and then consider each number one by one.
Okay.
For each number, we create new subsets by adding that number to all the existing subsets we've already built.
Right.
We're cascading our way to the full power set.
Let's break it down with our trusty example.
Yeah.
1, 2, 3.
Okay.
We start with our lonely empty set.
Yep.
Represented by,
Right?
then we bring in our first number, 1.
Okay.
We add it to our existing empty set, and boom, you have a new
Yeah.
subset.
Right.
1, now we've got 2 subsets in total.
Okay.
Next up is number 2.
Right.
We add it to both of our existing subsets,
Oh.
which gives us 2 and 1, 2.
Okay.
Your collection is growing.
Yeah.
1, 2, and 1, 2. We're on a roll.
And finally, the grand finale number 3.
Right.
We add it to all 4 existing subsets.
Yeah.
Which gives us 3, 1, 3, 2, 3, and 1, 2, 3.
Nice. We've successfully built all 8 possible subsets.
Boom! Give yourself a pat on the back.
Yes.
This cascading approach seems pretty straightforward.
It is.
It's like building a pyramid of subsets, with each level adding more elements.
Yeah.
But I have a feeling there might be some downsides lurking beneath the surface.
Yeah, could be.
What do you think?
You're right to be cautious.
Okay.
This method is great for grasping the basics of subset generation,
Right.
but it has a hidden cost.
Uh-oh.
Remember how the number of subsets explodes exponentially as the set size grows?
I do, yeah.
Well, this cascading approach has a time complexity of O(n) to n.
Oh, no.
That means the time it takes to generate all those subsets can skyrocket as your input set gets bigger.
So it's a good starting point for understanding the concept, but
Yeah.
maybe not the most efficient way to tackle larger sets.
Right.
We'll need to explore some more advanced techniques to keep those computation times under control.
Exactly. And that brings us back to our recursion hint.
Yeah. Are you ready to venture into the recursive maze and see if we can find a more elegant solution?
I'm always up for a good algorithmic adventure. Let's do this.
Awesome. We're about to venture into the world of recursion to tackle this problem head on.
Recursion, always a fun time. It's like that choose-your-own-adventure book
Uh-huh.
where each decision leads to a different storyline.
Exactly. In this case,
Okay.
our adventure is about deciding whether to include or exclude each element from our set as we build our subsets.
So how does this choose-your-own-adventure strategy actually play out in code?
Let's imagine we have a magical helper function that can generate all subsets for a portion of our set.
Okay.
We can use this function recursively to break down the problem into smaller, more manageable pieces.
I like where this is going. Let's say we have our set 1, 2, 3.
Right.
Can you walk me through how we'd use this recursive magic?
Absolutely. We'll start by calling our helper function with an empty subset and the entire set 1, 2, 3.
Okay.
Our function will then consider the first element, 1.
Okay, so we're at a decision point. Do we include 1 or not?
Right. We create 2 branches in our adventure.
Yep.
In one branch.
Yeah.
We include 1 in our current subset, so we have 1.
Okay.
In the other branch, we exclude 1 and keep our subset empty.
And then what? Do we move on to the next element too in both branches?
Exactly. In each branch, we recursively call our helper function again.
Right.
But this time with the remaining portion of our set 2, 3.
So in the branch where we included 1,
Yeah.
we're now looking at 1.
Right.
And trying to figure out how to combine it with the subsets we can generate from 2, 3.
You've got it. And in the branch where we excluded 1, we're still starting with an empty subset and doing the same thing with 2, 3.
This is starting to feel like a recursive chain reaction, where each decision spawns 2 new adventures.
That's a great way to visualize it.
Yeah.
Each recursive call breaks down the problem into smaller subproblems until we hit a base case.
A base case, that sounds important.
Yeah.
What exactly is a base case in this scenario?
The base case is like the ending of our adventure.
Okay.
It's the point where we've considered all the elements in our set and have a complete subset.
Okay.
At that point, we add that subset to our collection and backtrack to explore other branches.
Backtracking, that's the other key piece of this recursive puzzle, right?
Backtracking is how we rewind our adventure and explore all the alternative paths.
Gotcha.
Once we've explored both branches for an element, include and exclude, we back up and move on to the next element.
This backtracking mechanism ensures that we don't miss any possible subsets.
Exactly.
It's like making sure we've thoroughly explored every nook and cranny of our choose-your-own-adventure maze.
You nailed it. Recursion and backtracking work together to systematically generate all possible subsets without any duplicates.
Okay, so we've got a solid understanding of how recursion and backtracking can be applied to this problem.
Right.
But I'm curious about the efficiency of this approach. Is it any better than our cascading method?
Well, the time complexity of this recursive backtracking approach is still O(n)(2)n.
Oh.
Just like the cascading method.
So we haven't escaped the exponential beast yet?
Not quite.
Oh, man.
However, there's a subtle improvement in terms of space complexity. Instead of storing all the subsets at once, we only need to keep track of the current subset we're building as we traverse our decision tree.
So we're saving some memory space by not storing all the subsets in one giant collection.
Yeah.
That's a plus.
Exactly.
Okay.
But remember, that exponential time complexity still looms large as your set size grows.
Yeah.
The time it takes to generate all those subsets will increase rapidly.
Yeah, I can see that.
It's like trying to explore a maze that doubles in size with every step you take.
That sounds like a computational nightmare.
It can be, especially for very large sets.
Yeah.
And that's why even with a clever recursive approach, we might need to consider other optimization strategies to tame that exponential growth.
Optimization strategies. That sounds intriguing.
Yeah, it is.
Okay, so we've already talked about the cascading approach and the recursive backtracking method, both of which have their strengths and weaknesses.
Yeah.
But you've been hinting at something called bit manipulation. Is that the secret weapon we've been waiting for?
Bit manipulation is indeed a powerful tool in our algorithmic arsenal.
Okay.
It allows us to leverage the binary representation of data to perform operations in a highly efficient way. It might seem a bit like magic at first, but once you grasp the concept, it opens up a whole new world of problem-solving possibilities.
All right, I'm ready to embrace the magic. But can you break it down for me and our listeners?
Yeah.
How does this bit manipulation sorcery actually work in the context of subset generation?
Imagine each element in our set is like a light switch that can be either on or off.
Okay. Yeah.
We can represent the state of each switch using a single bit, 0 for off and 1 for on.
So if we have our set 1, 2, 3, we could represent the subset 1, 3 with the binary number 101.
Exactly.
Where the first and third bits are set to 1.
Yep.
Indicating that elements 1 and 3 are included.
Precisely. And the beauty of this representation is that we can use bitwise operations to efficiently generate all possible combinations of on and off states, which directly correspond to all possible subsets.
I'm starting to see the light, literally. But how do we actually generate these binary representations?
If our set has n elements, we need to generate all the binary numbers from 0 to 2n1. Each of these binary numbers will represent a unique subset.
So for our Tresky 1, 2, 3 example, we generate binary numbers from 00 to 111,
Right.
which is equivalent to decimal numbers 0 to 7.
Uh-huh.
That gives us 8 unique binary patterns
Right.
representing our 8 possible subsets.
Exactly. And for each binary number,
Okay.
we simply iterate through its bits.
Right.
If a bit is set to 1, we grab the corresponding element from our set and add it to our current subset.
Let's walk through an example to make sure I'm following.
Sure.
Say we have the binary number 101.
Okay.
The first bit is 1, so we include the first element from our set,
Yeah.
which is 1.
Right.
The second bit is 0, so we skip the second element.
All right.
And the third bit is 1, so we include the third element, 3.
Okay.
That gives us the subset, 3.
You've got it. Rinse and repeat for all the binary numbers from 00 to 111.
Okay.
And you'll have generated all the subsets of 1, 2, 3.
This is mind-blowing. It's like we've unlocked a secret code that allows us to manipulate subsets at a much deeper level.
I know, it's pretty cool.
But what about efficiency? Is this bit manipulation approach truly faster than the previous methods?
It is. The time complexity of the bit manipulation approach is still technically O(n) to n,
Okay.
but the constant factors involved are much smaller.
Right.
This means it's significantly faster in practice,
Cool.
especially as our sets grow larger.
So we haven't completely escaped the exponential growth, but we've found a way to make it much more manageable.
Yep.
That's a huge win in my book.
Absolutely. And it's a testament to the power of understanding the underlying binary representation of data.
Right.
It can lead to some surprisingly elegant and efficient solutions.
Well, I have to say, this deep dive into subset generation has been an incredible journey. We've explored multiple approaches, each with its own unique insights and trade-offs.
It has been fun.
Huge thanks to our listener who submitted this problem and sparked this amazing conversation.
Absolutely.
I hope you've enjoyed the ride as much as we have.
Yeah. Thanks for listening, everybody.
That's a wrap on this episode of AI.Code.Cast.
See ya.
We'll catch you next time with another deep dive into the world of algorithms and data structures. Until then, happy coding.